Hey guys, we're looking at section 7.1 as our second to last section. Um, the big thing about the last two sections is this is where we start to see some more capabilities in order to see how you could actually apply calculus to various realistic problems. Because so far what we've talked about, specifically when it comes to integration, we said the integration from things like a to b of f of x dx is our basic integral. We claimed that that was, in terms of the picture, represented by the function f of x sitting between our a value and our b value, and we said that it's the area in between these, which by itself is pretty neat. But you notice this is pretty heavily restricted, and so this is kind of the old way. And so you notice that this is bounded by a and b. This is the left bound and the right bound, but it's actually bounded by one more thing. It's bounded by the axis here. The bottom part of this shape is the axis. Remember we used that to chop it up into little pieces and then found it manually using Riemann sums? And then we looked at integrals as the faster way of doing that. And so rather than doing little bitty rectangles, we just did, an integral. Well, here's the funny thing. Anytime we talk about these area problems, it's important to note that this is not a common shape. Like, it's not common to see in realistic settings, like, shapes that are all wonky on two sides, but two sides are also nice. Even, like, nice on three sides. But the middle one does all kinds of fun stuff. Right? This isn't natural. This isn't normal. Like most shapes that you're going to see in terms of realistic settings, like think of something like a plane wing design. If you've never seen a plane wing design, it looks like so. You can clearly see that this doesn't fit these old narratives. Like the bottom isn't flat, the top isn't flat, the sides aren't flat. And so there has to be a way to get this in terms of an area. And so how do you find this area? Well, it turns out you do it in a very specific way. What you do is you look at the top of this graph as the function f of x. You look at the bottom of this graph as the function g of x. And as it turns out, how do you find the area of this space? You would integrate from a to b f of x minus g of x. In other words, for more complex shapes, you can find the area of a more complex shape by taking the top curve minus the bottom curve. And so this is kind of the new way, where instead of looking at it as, okay, we have one curve we're dealing with, one side that's doing crazy stuff, now the top and bottom can be both doing crazy stuff. Meaning I could have a shape that, the top is funky and the bottom has its own funky. And we can figure out the areas by saying, okay, let's just split the top and have it do one calculation and then have the bottom do a different calculation and then subtract those. Because think about it, in terms of the area, this is very helpful to see. So like here, you can see that it wants to know what this pink area is. So how does it find it? Well, it takes the entire area from top to bottom. So that would be just the area of the top curve. And then it subtracts away the pieces that are underneath the bottom curve. And so it takes this big piece first, that's f of x, and then it cuts out the bottom piece, g of x, giving us this newer shape, allowing us to take these new and unique ways to figure out what this piece is supposed to be. And so this allows us to find areas of regions bounded by two different curves, meaning we can take more and more advanced concepts. And so one of the fun things that's a fun little project you can do is there is actually an equation that gets you something relatively close to the symbol for Batman. It's a line escape in 2 dimensions for top and bottom. And you can actually do this by just taking this top piece and seeing it as, you know, f of x, taking the bottom piece as seeing it as g of x, and take f minus g, and integrate it, of course. It allows us to take and look at more and more complex circumstances to see how we can figure out which pieces are actually going to be our shape. And it allows us to see these as new possible curves. Because, like I said, more and more often you're going to end up with these kinds of shapes, where there's something happening on both the top and the bottom, not just something happening on just the top. And so it allows us to get these more complex shapes and to find their areas, just like we can find the areas of any shape. And it gets us more and more in that direction. This is best case here. It's not a theorem, it's just an idea. It's the area of a region between two curves. In order for this to work, it's important to note these have to be continuous in the interval that we're talking about. If there's any asymptotes or holes, this obviously won't work because you can't integrate, you know, the top curve by itself unless it's continuous. You can't integrate the bottom curve by itself unless it's continuous. And so that's an important note to make. They have to be continuous to make this work. And so what you do is you just integrate f of x minus f of g, which, if you remember your integration rules, this means you can do the integral from a to b of the top minus the integral from a to b of the bottom. You can, of course, split it apart if that's easier to do for the problem. So this is the only concept in this section. Like, there's pieces that talk about, you know, how you can look at it as a rectangle, and then those rectangles can be summed together. It's referred to as a representative rectangle, but it always leads back to an integral. That's where the idea comes from. And so how do we find a more advanced piece? Well, it helps to figure out some basic things today. The big questions about today are going to be questions about, well, what are my equations? The nice thing is this is usually given to you. And then secondly is, well, if I want to do this right, I need to know a top and bottom so I can put them in the appropriate place and actually integrate. So which one is top and which one is bottom is the other really big important question. Because if you put the wrong one in the wrong place, you're going to get a wrong answer. So if you put the bottom where the top should be and the top where the bottom should be, this answer will be wrong. So these are the big questions that are going to be pervading today, is how do you figure out these pieces? And then the bigger question is going to come later after we do a couple of examples about, well, it's not always as simple as this, where you have a clearly defined top and a clearly defined bottom. So how do you do it when it's even more complex, such as when these things cross? And that is going to be where we finish today. So our one major topic is this integration formula. We can find the area between two curves using both formulas for f of x and for g of x just by subtracting them. But now let's look at some examples. And we'll reference this part at the very end because this is really neat. Okay. Let's do number 8. So your homework, remember, is 7 through 13 odds and then 19 through 45 every other odd. You notice that for many of these, it says to sketch the graph of each function and shade the region. My big thing about that is I want to make sure that you use a calculator to sketch it. You don't actually have to draw the sketch, just use a calculator to sketch it for you. Because, quite frankly, we don't spend enough time sketching these graphs as it is in most cases, and so it's better just to get the graph from the calculator, which is what I'm going to do anyways. Okay, 8. We have in this function the integral from -1 to 1 of 2 minus x squared minus x squared dx. Now let's note some things about this formula. So in this case, these two numbers are my bounds. So this is left bound at -1 on the x-axis. It is right bound at +1 on the x-axis. And this tells me my top curve is represented by the function 2 minus x squared. My bottom curve is represented by x squared. So let's take a look at what we're looking at here. Now for this function, let me see, I've got my graph. I'll come back to this one later. Let's go ahead and add another one in here. My top one is 2 minus x squared, so 2 minus x squared, that's cubed, squared. My bottom one is just x to the second. And so you can see in here how between -1 and +1, there is a clearly defined shape, this little almost eyelid looking shape. And this region is the one we're going to attempt to fill in. And so how are we going to do that? Well, we're going to define from -1 to 1 of this first curve minus from -1 to 1 of this red curve. So again, it's always top minus bottom. And so top curve, 2 minus x squared, that's in black. Bottom curve is just x squared, that's there in red. Now, a few things to note here. Because this is written as a formula, we could immediately split it and integrate each one separately, or we are allowed to simplify this. Because remember, this is just algebra inside these parentheses. There's no calculus in these parentheses. It's only once we've taken these steps that we can then do the calculus afterwards. So one way to do this is I have option number 1, which is like the pure calculus way. I just immediately am like, okay, I'm going to do from -1 to 1 of 2 minus x squared dx minus the integral from -1 to 1 of x squared dx. And that's tempting, but man, that's bad. Like, use your algebra. You took algebra first for a reason. Like, simplify this thing if you can. Anytime it's possible, simplify this function. So 2 minus x squared would be equivalent to 2 minus 2x squared dx. And algebraically, this statement and this one are exactly the same, which means that this curve has the same area as this curve. And this one is also one that I can integrate fairly effectively. And so, when possible, simplify. It's just a good way to go. Okay? So now I've got my integral. I can now integrate. The 2 becomes a 2x. The 2x squared becomes 2 over 3x cubed. And we're evaluating from -1 to 1. And then, when we evaluate, remember, the first number is plugged in. Minus the second number. And from here, I can start to simplify some stuff. So 2 times 1 is 2, minus 1 cubed is 1, 1 times 2/3 is 2/3. Minus 2 times -1 would be -2. -1 cubed is -1, times -2/3 would become positive 2/3. We can then distribute the negative signs, giving me 2 minus 2/3 plus 2 minus 2/3. And so I end up with 4 minus 4/3, or 8/3, which means that the area between these two curves, this little space in between these two, is 8/3. And I can verify that using my TI-84. So remember, my TI-84 allows the ability to graph these kinds of functions. Oh, come on. There we go. To evaluate those manually. So I'm going to use the calc command. Oops. Need to put them in my graph first. Let's get these in. So I have 2 minus x squared, and then I have x, so I can calculate, get my graph in here. Ooh. Try to make sure to type it in correctly on the first try. Okay, let me get my zoom to standard. And so here's my graph. And so again, I'm trying to find this little area sitting between these two curves, a little spot right there. And if I want to do that, I can do a second calc. I can integrate with number 7. So I'm going to do my lower limit as -1, my upper limit as 1. And so it says for this first one, and we can zoom in and see, it did it for the blue one. And so you can see for that blue one, this piece is 2/3. So this one has an area of, so the x squared has an area of 2/3. Whereas for the red one, from -1 to 1, it have an area of looks like 3 1/3. And if you subtract those two, so you take these two, so it's 3 1/3 minus 2/3, you'd end up with 2 2/3, which is the exact same answer we got over here. And so yeah, this should represent the area, which is, you know, pretty neat by itself. To do that without using the graphing utility, I think is a little easier, but that's just me. So what you can do is you can hit the math button. Hit the math button. And down here it says finite integral, which is number 9. And so I go from -1 to +1 of, the first function was 2 minus x squared minus the second function, which was just x squared. We're doing it with respect to x. Boom. 2 2/3, exactly as we saw over here. And so, like, this is just really nice to do. Remember, that's under the math tab. It says fn int, which means finite integral, as opposed to definite integral. It's a finite and definite are, you know, the same thing. So there you have it, which is pretty neat. And so this tells me that the area of that little eye slit in that problem, so as represented by my Desmos graph here, that little eye slit right here in the middle is 8/3 or 2 2/3 in terms of area. So that's number 8. Example number 2. The same basic concept. The big tricks are going to be things like, can we identify the first curve or the top curve? Can we identify the bottom curve? And can we use that to figure out where our next piece is going to be? For this next one, we're actually going to do number 12. For number 12, we have the following problem. We have the integral from -pi/4 to pi/4 of secant squared of x minus cosine of x dx. Okay, so let's point out what each of these things means. And so for these first couple ones, it's actually asking us just to do the shading. And so for mine, we'll pull up my graph. Here we go. I actually found the answer. See? Read your directions, kids. Don't be silly. So my top curve should be secant squared of x. And then my bottom curve should be cosine of x. And it is from -pi to pi. And so, no, sorry, -pi/4. So pi/4, let's zoom a little bit, pi/4 is just a little less than 1. We're talking about this area, this bounded area. And so if I want to graph this thing, what would this look like? Let's get above the graph. So we have the secant squared And then on bottom we have the cosine. And the area we're actually finding is this almost bow tie-like shape between negative pi over 4 and positive pi over 4. So it'd be this shape. So here we want to find the area of a bow tie. Apparently you use secant squared and cosine. So that's it for number 12. Notice that it didn't actually ask us to find the solutions. It just said to, use the solution or use a picture to graph these and see how they work. So notice how we do that. We see the boundaries. That's the left and right hand side. So there's my left side, there's my right side. My top curve is the secant squared, so that's where the top one is. My bottom curve is the cosine of x, that's the bottom one, and it's the area in between those two, so I just shade in the region in between them. Okay. Yay. Read your directions. Don't be like me. Reading directions is for smart people. I'm apparently done. So let's do a real example where we actually get an answer that we're supposed to get, like number 20. I can get 20 right there. So we sketched and did number 8. We just sketched number 12 because that's all the instructions asked us to do. So let's look at number 20. 20 states we have sketch the region bounded by the graphs of the algebraic function, then find the area of the region. Yay! So we have two pieces. Y equals negative x cubed plus 3. We also have y equals x. And we have the range between x equals negative 1 and x equals positive 1. Okay, so let's go ahead and talk about this integral. So we're going to have the integral. Obviously the bounds are negative 1 and positive 1, but the question is which comes first and which comes second. So it's helpful at this point to do our graph. Well, let's make a graph. I go to my graph. And let's put these two pieces in. We have, for our first one, negative x to the third plus 3. And we have y equals x, so just x. So in this case, we're bounded between negative 1 and positive 1. So let me go ahead and give a quick rough sketch of this. So here in blue, I want to make my y equals x. There it is. That's pretty good. Here in red, I'm going to do my x over 3. There we go. And we're bounded between negative 1 and positive 1. So the space we're talking about is between here and here. So let me get this kind of weird little oblong shape here. It's got a little curved top and a smooth, almost triangular bottom. It's kind of like almost like a semi-trapezoid here. And so that's the piece we're trying to find. So we can clearly see that in this example, the blue line, the y equals x, is the one that is the bottom. And the red line, or the negative x cubed plus 3, is the top one. So now I can integrate. Once I've got my pieces, including my bounds, and I know that this should be the top one, this is the bottom one, I can just do a random integration problem. So this is the integral of negative 1 to 1. I can then distribute the negative sign, and I put negative x cubed minus x plus 3 dx. And now I can integrate. When I integrate, I would have negative x to the 4th over 4 minus x squared over 2 plus 3x evaluated from negative 1 to 1. And now I can actually plug some of those things in and start getting solutions. So remember, the first one is plugged in first, so negative 1 to the 4th power over 4 minus 1 to the 2nd over 2 plus 3 times 1 minus the second one, which would be negative 1 to the 4th over 4 minus negative 1 squared over 2 plus 3 times negative 1. There we go. And now I can start simplifying some stuff. Negative 1 to the 4th over 4. 1 to the 4th is 1. Over 4 is 4, so negative 1/4. Minus 1 squared is 1 over 2 is 1 over 2. Plus 3 times 1 is 3. Minus, okay, negative 1 to the 4th power would be positive 1 over 4 would be 4, negative 1/4. Minus, negative 1 squared would be positive 1 over 2. And then negative 1 times 3 would be negative 3. I can then distribute. I would get negative 1/4 minus 1/2 plus 3 plus 1/4, distribute the negative sign, plus 1/2 plus 3. I can then see that the negative 1/4 and positive 1/4 are going to cancel. Negative 1/2 and positive 1/2 are going to cancel, leaving me with just 6. So that means, as weird as this looks, the area bounded between negative 1 and positive 1 of this function is just 6. A nice round number. Which is neat, in my opinion. Like, you have this cool little curve thing going on here. Like, this little curve is supposed to give us some weird answers, and yet it doesn't. And if you want to see what this kind of looks like, you can do x equals 1 and x equals negative 1. Kind of the advantage of Desmos, and it's this middle area kind of filled in between all 4 of these lines now. So between negative 1 and positive 1, between x and negative x cubed plus 3. And so it's this space filled in between these, which is pretty neat. Nice try number 6, who would have thought? I'll do one more of the basics before looking at what an advanced problem can look like and kind of how to solve it. So let's look at one more of these. In this case, I'm going to go to 26, where they have not given us the boundaries for all the pieces, and we have to kind of infer it. Negative x squared plus 9 over 2x plus 1 is our f of x, and our g of x is equal to 1/2 x plus 1. Apologies. Go ahead and get rid of the screen. There we go. Okay, so we have negative x squared plus 9 over 2x plus 1, and then 1/2 x plus 1. I want to figure out how to write this in terms of an integral. So to write this as an integral, I need to know the left bound, the right bound, which of these comes first, in other words, is the top function, and which of these comes second as the bottom function. I need to fill in these 4 blanks. Well, let's take a look. So at this point in time, I'm going to pull back up Desmos. I'm going to type these functions in. With some functions, it becomes pretty obvious which one it means. With others, less obvious. Plus 9 over 2x. Oh. Plus 9 over 2x plus 1. That should mean x, whatever it is. X. Sorry. And then 1/2 x plus 1. Okay, so in this case, you can clearly see that there's a bounded region, but you'll notice this bounded region is not just bounded left to right, it's actually bounded fully by these 2 equations. So the left-hand side stops at 0, 1, the right-hand side stops at 4, 3, which means in order to fill out my equation over here, remember I have to use the left and right x values. So in this case, my x would be 0, and my x would be 4. I don't include this side because it's not bounded. If I was to zoom out, like there's no closing line, like there's nothing connecting these 2 ends to make a shape. So I can't really do it without doing it this way. I have to stop at 0, or start at 0, and I have to stop at 4, otherwise I have an open paint can, which is going to spill everywhere. And so it turns out this little space is the only space we're dealing with. It's this little space between this green curve and this purple curve. And so the green curve is our negative x squared plus 9 over 2x plus 1. And this other one is 1/2 x plus 1. Okay. So, like before, I recommend always simplify first. So this becomes the integral between 0 and 4. Negative x squared is negative x squared. 9/2 x minus 1/2 x would become 8/2 or 4. Positive 1 minus positive 1 would become a 0. And you end up with this equation, which is much nicer. Always simplify first if you can. From here, I can now integrate. So negative x squared becomes negative x cubed over 3. X to the fourth becomes 2x squared, divided between 0 and 4. And now I can start plugging in. So I plug in 4 first, so negative 4 cubed over 3 plus 2 times 4 squared minus negative 0 cubed over 3 plus 2 times 0 squared. Okay, 0 cubed is 0, divided by 3 is 0, negative of that is 0, 0 squared is 0, times 2 is 0. This other one just becomes 0. And let's look what happens to this first one. So negative 4 cubed is 64, so negative 64 over 3 plus 4 squared is 16 times 2 is 32. 32 expressed as a multiple of 3 would become negative 64 over 3 plus 96 over 3, which means my answer becomes 32 over 3. So make sure to sketch my area because it said to sketch it. So on my graph, I would have 1/2 plus 1. Just quickly making my graph. And then I have my negative. So between 4 and 0. And so the area we're looking at in particular is this region in between those. So there we go. And I can make sure my answer is actually correct by simply plugging that formula into my calculator, which I'm going to do now. Let's pull up my TI-84. So I do math, finite integral. So I go from 0 to 4 of, and my equation was negative x squared plus 9x, so in parentheses, negative x squared plus 9 over 2 x plus 1 minus 1 over 2 x plus 1 dx, which gives me 10.6 repeating, which is the same as 32 over 3. So there we have it. Okay, it worked. So what does a more complicated one look like? Like, this seems pretty straightforward. You just have to integrate a function, so that's not too bad. The trick is getting the top and the bottom correct, so that's not too difficult once you see a picture of it, and you got a graph to help you with this. And then you can simplify if you need to, which makes the problem a little easier to do, and then just plug and chug, and it's a lot of algebra work after that. So what's the trick? Like, what's supposed to be hard about this, Douglas? Well, some functions aren't so nice. So at this point, I want to take a look at a different function, and it's number 42. (42) is a little bit different. It says use a graphing utility to graph the region bounded by the equations, find the area of the region, then use the integration capabilities to verify your results. You should pretty much be doing this for every problem. But look at 42. We have fx is equal to, we have x to the fourth minus 4x squared. And we have g of x is equal to x cubed minus 4x. Well, I thankfully already have my graph made. So let's look at these two. Okay, so what's the problem? Well, you notice that there's actually 3 unique bounded regions. There's this first bounded region between -2 and 1. And you notice that in this bounded region, the purple one is on top and the green one is on bottom. There's a second bounded region, this one here, between 0 and 1, where the green one is on top and the purple one is on bottom. And there's a third bounded region down here. Notice that the region to the upper right, so this one up there, and upper left, the one over here, they're not bounded, so we can kind of ignore them. But there's 3 unique regions in this problem. Okay? These 3 unique regions, 1, 2, and 3, would be solved differently. So how do I write this? Like, how do I write that integral if I'm supposed to have an integral between a and b of top minus bottom? Like, how do I do that? What do I do if my top and bottom are not constant? Well, the trick is, you would just look at this problem and do it in 3 pieces. You can't do this from -2 to +2. Like, we can't just come in and say, I'm going to start at -2 and all the way to +2 as one integral, because it's going to do 2 of the places right and 1 of the places wrong. Because if you choose purple to go on top, then it's going to do the first piece right and the third piece right, but the second piece is going to get the wrong answer. And if you choose the green one to be on top, well then of course it's going to do the middle one right, but the first and third wrong. And so you kind of have to do this integral of the area. You have to do it in 3 pieces. The first piece we're going to do is between -2 and 0. And for this piece, the purple function is the one that's on top. So that'd be my x cubed minus 4x squared minus my bottom one, which in this case would be x to the 4th minus 4x squared. It should be x, sorry. So you have to do it from 0 to 2, from -2 to 0 as one thing. Then you have to add to that the second one, which is between 0 and 1, which would be the opposite. So it'd have the green one come first, because it's the one that's on top. The one that's on top would then be x to the 4th minus 4x squared minus x cubed minus 4x dx. And then add to that the last one, between 1 and 2, which would look very similar to the first one, just with different boundaries, of x cubed minus 4x minus x to the 4th minus 4x squared. And so rather than be able to do it in one piece, we have to look at it as 3 distinct pieces, because again, it has to always be top minus bottom. If the top and bottom are not constant, you have to break it into components. So if I wish to do number 42, what I have to do is, I have to do it in these 3 pieces. And so I have to be able to solve part 1 and get a solution, solve part 2 and get a solution, solve part 3 and get a solution, and then just take those answers and of course add them together to get the total area. It's the only way. And so it becomes really important to be able to see the picture to see which one's on top and bottom, which is why Graphing Calculator can be so very helpful. Now, I'm actually going to use my graphing utility to do all this for me because I'm lazy. But, you know, you should do it by hand as well. When you do this, extra practice would be to do it by hand. So please make sure you're doing those. But I'm going to take the shortcut. So this would tell me I would take the integral from -2 to 0 of x to the 4th, x to the 3rd minus 4x minus x to the fourth minus 4x squared parentheses dx. Oh, what did I do? No. Should stop at 0, not 2. What are you doing, Douglas? You crazy. Oops. No. 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 0. No. Good. I hate all things. 0. Yes. So let's give you one answer. I'm then going to add to that the integral in the other form from 0 to 1 of the next integral, which would be the opposite order, x to the fourth minus 4x squared minus x to the third minus 4x dx. So we add the second integral, and then we would add to that the third integral. So math, integral, so between 1 and 2 of, this is getting annoying, x to the third minus 4x minus x to the fourth minus 4x to the second dx. So the overall integral should be 9.76 repeating. And there it is. So this allows us to take more advanced shapes that don't follow the traditional rules, like this one that clearly does not follow those traditional rules, like top and bottom switch. And so it allows us to do it by just looking at it as segregated pieces. And this is the last major component. Before I end today, with the remaining minute of time I'm going to take, I do want to point out that this is the first time it's really mentioned in the text, but you can do it both ways. In this case, you can see how they've taken these expressions and written them in terms of y. So you notice that for this expression, they've used g of y and f of y. Notice that what that does is it just changes your integral to be in terms of y. And so notice the boundaries are also in terms of y. So the y value is -2. The y value is +1. So you can do an integral in terms of y just like you do anything else. But notice how it changes your representation of which one's on top and which one's on bottom. Your top value is one that's farthest away from the axis, so it's actually farther right. And your bottom one is the one that's farthest left. So top and bottom becomes right and left. And so it's just a different way, because this one is actually solvable by standard algebraic techniques, whereas this one is actually a lot harder to do by comparison. Like, look at the integrals for this one and how easy they are to do compared to the integrals for this one, which are much harder to do. And so it is considerably possible to do it in a different variable and actually make the math easier to do. We don't talk about this, and it's not on your AP exam, and it's not on your test. It's not even in your homework. But do note that that's the future. If you're going to go farther in calculus, you're going to see math in other variables. And it doesn't change the math, it just changes how you look at it. So instead of seeing this with x's and y's, like these g of y and this equation are the exact same equation. Like these two are the exact same as this one. And this f of y and this y equals, they're the same equation as well. They give you the same graph if you graph them. But the math associated with them, one, the math is much easier, one, the math is much harder. And so it's just a different way of looking at it, a different approach to it. And so always consider those facts whenever you have those kinds of problems. So there you go. That'll be it for today. Just under 45 minutes. We got one section left. I'll be posting that soon, and I'll see you guys next time.